Today we'll be doing the integral from 0 to 1 of the arctangent of x times the natural log of x divided by x dx. And to start off, we'll make a substitution. So we're going to let y equal the natural log of x, but that means that e to the y is equal to x, and it follows that dx is e to the y dy. The bounds of integration, y1 is negative infinity and y2 is 0, and that means that dy equals 1 over x dx. So we're going to have the integral from minus infinity to 0 of the arctangent of e to the y times y dy, and from here we will use integration by parts. So we're going to let u equal the arctangent of e to the y, but that means that du is equal to 1 over 1 plus e to the y quantity squared times e to the y dy, and dv is going to equal y, so that means that v is y squared over 2. So we're going to have the arctangent of e to the y times y squared over 2, evaluate it from minus infinity to 0, and then minus the integral from minus infinity to 0 of y squared over 2 times e to the y divided by 1 plus e to the 2y dy, and this limit ends up being 0. We could pull the negative a half to the front. So we're going to have negative a half, the integral from minus infinity to 0 of y squared times e to the y divided by 1 plus e to the 2y dy, and from here we'll use series expansion of 1 over 1 plus e to the 2y. So we're going to have 1 over 1 plus e to the 2y is the sum from 0 to infinity, negative 1 to the k e to the 2yk. So replacing that into the integrand, we have negative a half, the integral from minus infinity to 0, y squared times e to the y, and then the sum from 0 to infinity, negative 1 to the k e to 2yk times dy, and then swapping the sum and integral, we're going to have negative a half, sum from 0 to infinity, negative 1 to the k, and the integral from minus infinity to 0, y squared times e to the y, and then times e to the 2yk dy. But we could combine those exponents, so we're going to have negative a half, sum from 0 to infinity, negative 1 to the k, and the integral from negative infinity to 0 of y squared times e to the y times 2k plus 1 dy. And from here we'll make one last substitution. So we're going to let negative z equal y times 2k plus 1. So that means that negative dz is 2k plus 1 dy. So that means that negative dz divided by 2k plus 1 is equal to dy. Solving for y, we're going to have y is negative z divided by 2k plus 1, and z is negative y times 2k plus 1. So the bounds are going to be z1 is positive infinity and z2 is equal to 0. So we're going to have the integral from infinity to 0, and we're still going to have the sum from 0 to infinity, negative 1 to the k, and then the extra negative a half, and then negative z squared divided by 2k plus 1 quantity squared e to the negative z, and dy is negative dz divided by 2k plus 1. And we'll use this extra negative to flip the bounds of integration. So we're going to have negative a half, sum from 0 to infinity, negative 1 to the k, and the integral from 0 to infinity of z squared divided by 2k plus 1 quantity squared e to the minus z power dz divided by 2k plus 1. And then we're going to have negative a half sum from 0 to infinity, negative 1 to the k divided by 2k plus 1 quantity cubed, and then the integral from 0 to infinity of z squared times e to the minus z dz. But this integral is just the gamma function evaluated at 3, which is 2 factorial, which is equal to 2. So we're going to have negative a half sum from 0 to infinity, negative 1 to the k divided by 2k plus 1 cubed times 2. But this cancels with that 2, so we're left with negative the sum from 0 to infinity, negative 1 to the k divided by 2k plus 1 cubed. So we just got done showing that the integral from 0 to 1 of the arctangent of x times the natural log of x divided by x dx is equal to negative the sum from 0 to infinity, negative 1 to the k divided by 2k plus 1 quantity cubed. And to start off, to evaluate this sum, we're going to make the observation that negative the sum from 0 to infinity, negative 1 to the k over 2k plus 1 cubed is the same thing as negative 1/2 the sum from minus infinity to infinity of negative 1 to the k divided by 2k plus 1 cubed. And this could be further simplified into negative a half sum minus infinity to infinity, negative 1 to the k divided by 2 cubed times k plus 1/2 quantity cubed. So we're going to have a minus 1 over 2 to the 4th. The sum from minus infinity to infinity of negative 1 to the k divided by k plus 1/2 quantity cubed. So we have a minus 1 over 16 sum from minus infinity to infinity of negative 1 to the k divided by k plus 1/2 quantity cubed. And to evaluate this, we're going to make use of an identity. So it says that the sum from minus infinity to infinity of negative 1 to the k times f of k is negative the residue of pi cosecant of pi z times f of z at z equals z naught. So applying this to our sum, we're going to have negative 1 over 16 sum from minus infinity to infinity of negative 1 to the k and then divided by k plus 1/2 quantity cubed is going to equal negative times minus 1 over 16, and then we're going to have the residue of pi cosecant of pi z divided by z plus 1/2 quantity cubed at z equals minus a half. So these negatives end up canceling, and now we have to figure out this residue. So we're going to have a 1 over 16, and we're going to have a 1 over 3 minus 1 factorial, and then the limit as z approaches negative a half of the second derivative with respect to z of pi cosecant of pi z. And we could factor out this pi, and 3 minus 1 factorial is 2 factorial, which is 2. 16 times 2 is 32. So we're going to left off with pi over 32. The limit as z approaches minus a half of the second derivative with respect to z of the cosecant of pi z. And evaluating that first derivative, we're going to have a pi over 32. The limit as z approaches minus a half of the first derivative of the derivative cosecant of pi z is negative cosecant of pi z cotangent of pi z times pi. We can factor out the minus pi, so we have a minus pi squared over 32. The limit as z approaches minus a half of the first derivative of the cosecant of pi z times the cotangent of pi z. And I'm going to label this f and g, and we'll differentiate this via the product rule. So we have a minus pi squared over 32, the limit as z approaches minus a half of, we're going to have a g f prime plus f g prime. So we have minus pi squared over 32, the limit as z approaches negative a half of cotangent of pi z. F prime is going to be negative cosecant of pi z, cotangent of pi z times pi, plus f, which is cosecant of pi z. G prime is negative cosecant squared of pi z times pi. So cleaning this up a bit, we're going to have a minus pi squared over 32, the limit as z approaches negative a half. We're going to have a minus pi cotangent squared pi z and times cosecant of pi z, and we'll have a minus pi cosecant cubed of pi z. So now plugging in the limit, we're going to have a minus pi squared over 32, and then we're going to have a minus pi cotangent squared of minus pi over 2, cosecant of minus pi over 2, minus pi, we have the cosecant of minus pi over 2 cubed. The cotangent of pi over 2 is 0, so this whole thing ends up being 0. And we have a minus pi squared over 32. We're going to have a minus pi, and we'll have a negative cosecant of pi over 2 cubed. The cosecant of pi over 2 is 1, and negative 1 cubed is negative 1. So we're going to have a minus pi squared over 32. We have a minus pi times negative 1, but these negatives end up canceling. And multiplying by the pi, we're going to have a minus pi cubed divided by 32. So now we could say that therefore the integral from 0 to 1 of the arctangent of x times the natural log of x divided by x dx evaluates to minus pi cubed divided by 32. So that is the final result. Thank you very much for watching.